So last time it started talking about how to go about the business of extrapolating from gravitational wave sources that one thinks one understands in the Milky Way to extrapolating to the rest of the universe. And the crucial point was that there is no typical galaxy. You cannot assume that the Milky Way is a typical galaxy and then multiply by a number density of galaxies, because galaxies have a range of masses over a factor of 10 to the 4 or more, and they have very different star formation histories, very different stellar populations, and so it is completely inappropriate to just multiply by some number density of galaxies. On the other hand, if you think you understand the typical ages of the systems that you're interested in and the masses of stars that they're formed from, so far as we can tell, it appears that, except perhaps in the very early universe, if you take a few thousand solar masses of gas and you let them form stars, they seem to form about the same types of stars pretty much everywhere. And therefore, the best we can do at the moment is to assume that the star formation in terms of binary parameters and masses of stars that are formed are typical in our galaxy and everywhere else. And so if you identify the subpopulation of our galaxy, which the stars you're interested in are coming from, like young stars or old stars, then you can multiply by the star formation rate in our galaxy compared to that in the universe and get an extrapolation to the rate of the events you're interested in over the universe. So last time, I guess this is if the rate that you're interested in is from fairly young stars, for which the current galactic star formation rate is the relevant thing, then the rate per unit volume in the universe, which I'll denote by a curly r, is about 10 to the minus 2 per cubic megaparsec times the rate in the Milky Way. Milky Way, where this is in units of per year. Okay, so there are now two ways that you can then go about trying to figure out the event rates of interesting objects for LIGO or LISA or any other gravity wave experiment. One would be to try to get observations of the objects you're interested in, or progenitors of the objects you're interested in. Try to use those observations to extrapolate to get the rate at which those objects are merging in the Milky Way, and then this will give you the rate at which they're merging in the universe. The other way to do it would be to have great confidence in your theoretical abilities and lay down a population of stars, evolve them all, let everything happen to them, and calculate the final states of the progenitors, calculate the rates at which neutron stars or black holes will be merging in the universe, in the Milky Way, and then extrapolate to the rest of the universe. Unfortunately, both of those techniques leave something to be desired. On the observational side, there are many selection effects. You can't see all of the things you're interested in, just the bright ones that are nearby, that are in long enough orbits that they're not smeared out, which are in the hemisphere, for which you have telescope time, et cetera, et cetera, et cetera. And on the theoretical side, there's the difficulty that, well, I should say on the observational side, perhaps there are also some things which you would be interested in, but which you can never have a hope of seeing or have not yet seen. For example, binary black holes, very difficult to detect electromagnetically. Black holes plus neutron stars should be detectable electromagnetically, but we've never found any, despite having found 1,300 neutron stars. We never found one with a black hole companion. They ought to exist. They ought to be very common. We've never found one, so we can't figure out rates, and we certainly have never seen any black hole binaries. So that leaves the theory, and the theory, as I will tell you, has, unlike for single stars, has lots of complicated three-dimensional radiation, hydrodynamic effects, and all kinds of things which are very magnetic braking. Magnetic fields are important. Shock waves are important. Things that are very difficult to calculate theoretically are very important, and therefore you have to make guesses about them, and you can try to make the guesses consistent with what you know about observation, but there's still it's still a little bit of a parameterized business. So neither of the theory nor the observations are clearly the way to go. So what we'll do is use a combination of them to try to do the best we can. So let me start off, as all good astronomers should, that nothing exists unless it's been observed. So let's try observed sources or progenitors of sources. And on the handout I gave you today, I gave you a list which is almost but not quite complete. I got bored with some of these neutron star plus brown dwarf systems since there are about a dozen of them, so and they're all pretty much the same, so I skipped them. But this lists all, as of this month that I knew about, double white dwarf systems, white dwarf plus hot progenitors of white dwarfs, that's white dwarf plus SDB, or the white dwarf plus brown dwarf, those are called AMCVN systems. Low mass X-ray binaries, that's neutron stars plus, in this case, white dwarfs that are filling the Rush lobe. And then down in the bottom I've listed the systems which are discovered as radio pulsars, which also contain some neutron stars plus white dwarfs, in that case not filling the Rush lobe. So you can see the statistics are not great. You don't have hundreds of each kind to do good statistics, but you have a handful of each type. So what's the first problem? Well, the first problem is that the Milky Way, let's draw it like this. Here's the galactic center. Here is the sun sitting off in the boondocks, 7.5 kiloparsecs from the center. And for a multitude of reasons which depend on wavelength in the optical, it's very hard to discover white dwarfs because they're very faint. So unless you have enormous amounts of observing time on enormous telescopes, you only find the white dwarfs which are nearby, say in a little circle like this. And that's all the white dwarfs you can ever hope to discover. And even if you got very big, much bigger telescopes, you probably couldn't discover them in a circle much bigger than this because the galaxy is so heavily extincted by dust that even with an arbitrarily large telescope, you're never going to be able to see more than a few kiloparsecs away. So we can count the white dwarfs in this region, and we can look and see if they have binary companions with orbital periods that are short enough to be interesting. And that in itself is quite difficult, requires lots of spectroscopy with large telescopes. You're interested in orbital periods which are short, and therefore you have a problem that if the orbital period is a few hours, you can't take exposure for longer than about 5 minutes, or the spectral lines get smeared and get very hard to detect. And in 5 minutes on a 17th magnitude white dwarf, it's very difficult to get a good spectrum, and the lines are very broad. And so you need big telescopes, and this isn't the most exciting thing you could imagine doing. It's not cosmology, so you only get 2 nights a year, and if it's cloudy, et cetera, et cetera. So Tom Marsh is the person who mostly does this, and he's discovered 4 of these systems. And he had the brilliant idea. Previous people have devoted far more telescope time looking at hundreds of white dwarfs, trying to find these systems, and found none. He had the bright idea of looking at white dwarfs with low gravity, which meant that they were helium white dwarfs, therefore they must have been, according to theory, in binary systems. And so far he's been batting 100% and finding those in binaries, despite other people who looked blind at 300 and didn't find any binaries. So some intelligence will help your batting average with the telescopes. In the case of radio pulsars, there's a very wide range of brightness, and for the faint radio pulsars, you can only see them nearby because your radio telescope isn't big enough to see them far away. There are also some very bright pulsars, which are rare but unusually luminous, which you can see at a large distance, unless that distance happens to be towards the galactic center, and there's a lot of plasma between you and the galactic center, which smears out the pulses and makes the sources not pulse anymore, and therefore not be detectable as pulsars. So once again, in the surveys, you're limited to some strange shaped volume in the galaxy. So this is a simple example. Let's suppose, let's suppose that we count up all the things that we're interested in inside a little spherical volume near the sun. And let's suppose that the objects that we're interested in, let's call them double white dwarfs, for example, are uniformly distributed in the galaxy, and we want to figure out how many there are in the galaxy. Well, the first thing is obvious that for each one that you see, the number in the galaxy is equal to the volume of the galaxy divided by the largest volume in which you could have detected your source. So this will be V max, And the way you play this game is you might actually discover, you might do a survey down to some flux limit, and you might discover the source several times brighter than the flux limit, but you could have seen it to a much larger distance, and therefore the correct volume, if you observe down to some limit, and you wanted to ask how many sources are there in a given volume, the appropriate volume is the volume in which you could have seen any of the sources you discovered. So let's call that V max. Then V over V max is the number of systems in the galaxy, and if you put a subscript I for each source, you add up all the sources you discover, and the sum of V over V max for each one is the number in the galaxy. Now there's obviously one thing that I put in here, which is the volume of the galaxy. Okay, now how do I decide what the volume of the galaxy is? Maybe I should have drawn this box twice as big. It would have been twice as many sources, right? So there's some observation in theory that has to be folded in here already, because you have to decide what the distribution of sources in the galaxy is. How high above the galactic plane do they go? What's the radial distribution? And when I write this down, you can see I'm implicitly pretending that they're uniformly distributed through this box, which is never true for any source that we know about. So a slightly more honest thing to do, and that's to do an integral over the galaxy of some model density. So if the sources you're interested in, you imagine that they have some rho of r density in the galaxy, and then you divide over by the integral of rho sub I of r d cubed r integrated over the volume in which they're detectable. Okay, and this is the factor by which you should multiply each source that you find to get the total number in the galaxy. And obviously, if these rows are constant everywhere except some boundary with hard edges, then this integral just gives me the volume in the galaxy, and this integral just gives me the volume in which they would have been detectable, and it reduces to this expression. But in general, there's some radial profile and some profile in the vertical direction and so on, until you actually do these integrals. Okay, so that's the observed sources. And now it often happens that for every observed source, you have some theoretical reason to believe that there are a whole lot of invisible sources. So for each one of these visible ones, you should multiply by some factor to take account of the invisible ones. And so, for example, in the case of radio pulsars, the invisible ones, a radio pulsar is believed to consist of a spinning magnetized neutron star, and the emission is coming out, the radio emission that you see is coming out along the magnetic poles, and you will only see the source as a radio pulsar if the Earth happens to lie in a direction where this cone will intersect the Earth. So for those sources in which the Earth happened to be located over here, rotate the source, it's harder to draw that, we would never detect it as a radio pulsar because the beam never intersects our line of sight. So for every one of these ones which happens to be oriented in the sky so that the beam crosses the Earth, there'll be some number of other ones where it doesn't. And of course you have to make models of the shape of this beam and the shape in this direction as well as in this direction in order to try to figure that out. And those shapes are clearly functions of the orbital period and the magnetic field of the pulsar, and so you have to try to fold that in. But for radio pulsars, popular numbers are the so-called beaming fraction. F is somewhere in the range of 1/2 to 1/10. And there's been some recent arguments that for the types of pulsars that are one's interested in here, maybe 1/5 or 1/6 is a good number, but there are people who will dispute that. In the case of white dwarfs, it's a little bit less obvious, but there's an analogous effect. So that is that many of these systems which are discovered, these white dwarfs and white dwarf plus SDB stars, when you look at them, you will discover, if you look at this column over here, which says the time to merge, so that's the time it will take gravitational radiation to merge these two systems up into the LISA band, for example. You see that those numbers are several 10 to the 8th years. On the other hand, most of these white dwarfs have ages which are less than 10 to the 7 years. So it might seem a little strange if you're looking at these systems which have another several 10 to the 8th years to go, why do you always find them when they're 10 to the 7 years old? Well, the answer is that white dwarfs fade as they cool. And therefore, if you do a volume limited sample, you can see the bright ones in a much larger volume than you can see the faint ones. And so they tend to dominate your sample. So the result of that is that you can sort of think of it in two ways. One is the right way to calculate a rate is to divide not by this merger time, but by the actual age of the white dwarf. But another way to think of it is for every bright young white dwarf that you see, there are a whole bunch of faint cold ones which you couldn't see. And you can sort of treat that as a beaming factor, or you can do a more sophisticated analysis. But once again, there's a factor of several that you put in to account for that luminosity evolution of the white dwarfs. So the final birth rate, which in steady state is equal to what LIGO and LISA are usually interested in, which is the death rate, is then equal to the sum over all the sources you find of this volume factor psi sub I divided by this beaming factor or invisibility factor, or the extra ones that you can't see but should count. And then you have to divide to get a rate by the lifetime of the source. And the lifetime of the source that you want to put in here is the time since birth plus the time to merge. So that's the total lifetime. So for each source you see it sometime after, and by birth I mean birth is one of these systems which you're trying to count, not birth as the main sequence stars. So for example, if you look at a pair of white dwarfs, what you care about is the time since the most recently formed white dwarf formed, plus the time it has to go to merge. That's how long it would have been a double white dwarf system. Or for a radio pulsar, that would be the time since the neutron star you're seeing was created, plus the time that the system has to go till it merges through gravitational radiation. Okay, so for example, let's just take the double neutron star systems, for which this was the first set of sources for which this sort of analysis was done. So you see that there are 3 of them. The first 2 are in our galaxy, and the third's in the globular cluster. And I won't say very much about the globular clusters, except that one can do a similar analysis. You can work out the number of globular clusters around our galaxy and then compare to the number density of globular clusters in the universe. And then you have to be careful because usually the interesting objects are only in the very dense globular clusters, so you should actually only count dense globular clusters. But let's ignore the globular cluster system. So for the neutron star plus neutron star systems, there's 2 of them. There's 1534 and 1913 plus 16. And for this one, the psi sub I, and you will appreciate that in deciding these volumes, there's some reasonable astrophysicists could have disputes about these factors because they might disagree on what the vertical velocities of pulsars were and therefore how high they get. They might disagree about the radial distributions of pulsars. They might disagree about the luminosity function of pulsars, how faint is the faintest pulsar, etc. And all of those come into estimating this. And for 1913, that factor is something like 50. And let's use the popular beaming factor for both of them of 1/6. And the lifetime, and we'll estimate the time since birth is 2p over 2p dot plus the time to merge. And you have to be a little bit careful about this. This would be true if you could always see them, but of course probably there's some luminosity evolution associated. When the pulsar was younger, it was probably brighter. And as the pulsars get very close to the end of their merger, they would have orbital periods so short that you couldn't detect them by traditional radio astronomy techniques, where, again, if the orbital period is 1 minute and you have a 5-minute integration time, you don't detect it as a binary because it's smeared out. So there's some slop at either end of this, but again, it's not so bad as the slop in these other things that we're putting in. So for this source, that's about 2.7 by 10 to the 9 years. And for this source, it's about 4 by 10 to the 8th years. So our birth rate, neutron star plus neutron star birth rate in the Milky Way, estimated, as all brave astronomers do, from a grand total of 2 discovered sources. And that's what we've discovered in 30 years of hard work with radio astronomy is 2. Best we can do. So we have sum of psi I over fi tau. So that's 150 times 6 over 2.7 by 10 to the 9, plus 50 times 6 over 4 by 10 to the 8th. And it turns out that the two with those numbers have comparable contributions, and it's 1.1 by 10 to the minus 6 per year. In the Milky Way, and last time I told you that number, so that number now gives the rate throughout the universe, if we extrapolate with this blue star, of 10 to the minus 8th per cubic megaparsec per year. And so if we now are interested in when does 4 pi thirds r cubed times little r equals 3 per year, if I want to design an experiment which will see a few objects in a graduate student lifetime or a congressional staffer's attention span, we need to arrange this, and this is 10 to the minus 8th. So that says that r cubed needs to be like 10 to the 8th megaparsec. So r needs to be about 500 megaparsecs. 4 is equal to 3.
Congressional staffing skills when you tell them 4 is equal to 3.
Oh, well, they're used to that, right? 4 billion, 3 billion bucks. What's the difference, right? Yeah, I mean, you can consider the change in the NIH budget this year is larger than the NSF budget. The increase in NIH's budget to save the congressional, not the staffers, but the congressmen from their heart attacks, right? It's worth another $5 billion for NIH this year. Okay, so that's the example for the double neutron star system. So just for example, let me just go through the white dwarf plus white dwarf and subdwarf B stars. So these are very hot white dwarfs which are cooling down to become white dwarfs. And if you look at that table, you see that there's Twiddle's 5 systems in roughly 100 parsecs squared times pi. So that's in a little circle in the galactic disk with a radius of about 100 parsecs. And the radius of the galaxy we might take to be pi times 10 kiloparsecs squared. So if there's 5 in this volume, there must be about 5 by 10 to the 4 in the Milky Way. And the reason I'm doing this so sloppily and not being very serious about calculating these psi's is for 2 reasons. One, the distances to these systems are not known typically to a factor of 3, so it doesn't make a whole lot of sense to go doing solemn analyses. In the pulsars, one has a distance estimate based on the dispersion measured, which sometimes could be wrong by a factor of 3, but usually probably is not. In these cases, the distances are very much worse. So the sloppy analysis is really all that's justified, although fancier ones have been done. And you'll see that the younger systems have merger times which are of order 2 by 10 to the 8th years, and I told you that many of them are much younger, so we should put in a correction factor for the dark ones, dark, cool white dwarfs that we can't see. So if we take 5 by 10 to the 4 divided by 2 10 to the 8th years, we get a birth rate, so white dwarf plus white dwarf systems of 5 by 10 to the minus 3 per year. And then we should multiply this, so this is a raw rate. And then if one tries to account for the luminosity evolution, the old white dwarfs that are too faint to be detected in this volume, but would have been, the best guess is that it corresponds to multiplying by a factor of 2, and the actual rate is about 2 by 10 to the minus 2 per year. This one, in this case, the theory is actually a bit better than in most of these other cases, and the theory predicts a merger rate of roughly 1 per 30 to 1 per 100 years, and this is 1 per 50 years. So theory and observation are in rough agreement in this case.
What was the factor of 2 there?
Factor of 4?
No, the factor of 2 in the R. We went from 5.
That's factor of 4, right?
Okay.
5 10 to the minus 3 to this. It's the analog with the beaming correction. The point is that there's several ways of thinking about it. The typical so in calculating 5 10 to the minus 3, I took this number in the galaxy and divided by the times to merge, assuming that the white dwarfs were all quite young, which is true. So this is the appropriate estimate of the lifetime here. But the problem is that these systems that are seen in 100 parsecs are all very young ones, and you could only see them at that distance, not for this full merger lifetime, but for the first quarter of their lifetime when the white dwarfs are bright enough to be easily detectable in this volume. So it's not actually right to calculate that as a rate, because what I should really be doing is for each one of these young ones, I should put in the time that they're actually observable, which is much shorter than this estimate. So I put in that factor of 4 basically to correct for that, to say that the time that they're observable is about 5 by 10 to the 7 years due to white dwarf cooling. And a more sophisticated analysis would put in a theoretical model of the white dwarf cooling plus the observational selection effects and try to find the volume as a function of age for which you would find each one of them. Okay, and finally, let's look at the neutron star plus white dwarf column. So that's this column, NS plus WD, and those evolved into the last column, NS plus BD, probably. And if you go through the same analysis, the rate is completely dominated by the first source, which was discovered last year. So up until last year, this was believed not to be a very important channel, but with the discovery of this source, and the reason that source is so important is that this first source, although the merger time looks like a relatively boring 6 by 10 to the 8th years, the age of the pulsar is only 1 million years old. And the pulsar is a young firstborn pulsar, which everybody is quite convinced will disappear off the death line in less than 10 to the 7 years. And therefore the birth rate is jacked up by the fact that the lifetime of the observable pulsar is very short. So by the time the system merges with the white dwarf, it will be unobservable as a pulsar. But the fact that the radio pulsar was discovered, and it's a very young, very bright radio pulsar, means that the rate is quite large. And so if you go through to the best estimate, the rate is about 10 to the minus 5 per year in the Milky Way. And it's mainly from that pulsar 1141 minus 6545, for which the characteristic age is 10 to the 6 years. And this is a typical firstborn radio pulsar, 10 to the 12th Gauss, 0.4 second spin period. Unlike the other ones, which are all recycled pulsars with much longer lifetime. Now there's another category, as I mentioned, there are about a dozen of these neutron star plus brown dwarf systems. And many of these look interesting in the sense that if you saw them, they have companion masses that are a few hundredths of the solar mass, about 20 times the mass of Jupiter. And if you calculate the merger times, they're all less than the age of the universe, which sounds like those might be interesting sources. The difficulty is that there are two difficulties. First of all, in some cases, the measured orbital p dot has been measured, and the orbital p dot is on orbital period derivative is on a time scale much shorter than this by 3 orders of magnitude, has the wrong sign, And there's also all of these systems the pulsars are eclipsing, and the reason it's believed they're eclipsing is they're not being eclipsed by the companion, but by the wind they're evaporating from the companion. So it seems likely that in all of these cases, what's actually going to happen is that this little brown dwarf planet is going to be evaporated by the radiation from the pulsar before it ever gets a chance to merge. So they're probably not interesting as LISA sources. But the sources like these actually are interesting as LISA sources. They'll end up in the same frequency band as these, limited by the radius of the white dwarf, but their rate is much lower, so LISA will find a few of them, but they won't dominate the rate. Okay, now so those are essentially the three classes of sources which we know about and have enough observational data to predict rates. So from this rate, one could, for example, predict the LISA background from white dwarfs in the galaxy and the number of double white dwarfs which one would see with LISA, and from that one has a prediction for LIGO. But one should beware a little bit that you might be missing some objects, and let's forget about the double black holes, which we obviously haven't seen, or the black hole neutron star systems that we haven't seen. And let's just ask, suppose we were looking for neutron star plus neutron star systems, are there some kinds of sources that we might miss which might dominate the rate? Well, the rate of the ones that we see is about 1 every 10 to the 6 years, and the lifetimes of the sources are 10 to the 8th years or more. Now suppose that nature decided to create a class of double neutron star systems which initially were born with orbital periods of 5 minutes instead of several hours. Their lifetime to merge would be only, let's say, 10 to the 4 years when they were created. And if you made one of those every 10 to the 5 years in the Milky Way, the expectation value of the number which you could expect to find in the Milky Way would be 0.1. Namely, typically there wouldn't be any in the Milky Way, but you're making one every 10 to the 5 years. So they're actually being born at 10 times the rate of all these systems that you see. But you don't expect to see any. So you always have to watch out that especially when you're doing your theoretical models, you should keep track of whether there's the detectability in numbers of systems, because your rate can be dominated by systems which you have no hope of ever observing in the early phases of their life, but they might actually dominate the rate of death which you would see with LIGO and LISA or some other gravity wave detector. So you should keep that in mind. Okay, so what are we going to do about all these exciting black hole systems? Failed to detect any. So now it's up to theory. And it's also up to theory to try to tell us about these rates which might dominate but produce systems that we can't actually observe. Okay, so to do that, we're going to need to know a little bit about stellar evolution. And in the handout that I gave you last time, I gave you a potted 3-page summary of everything you need to know about stellar evolution. If you want to know a little bit more, you can take AY 123 next term, which will give you sort of the basis for this information that I handed out, but again will be far too little to actually give you a reasonable understanding. So there's lots of information, and this is a bare minimum. So on one page I gave you this sort of little brief synopsis of what stellar evolution is like as a function of stellar mass, and the number of critical masses. For example, objects less than about 0.08 solar masses as they contract, they get supported by degeneracy pressure before their centers get hot enough to support nuclear reactions, and therefore they never start nuclear reactions, and they just inexorably cool down after they're formed, and those are called brown dwarfs. They never ignite nuclear burning in their centers, except if above 0.05 solar masses, they briefly fuse their deuterium. Now, below about 0.3 solar masses, all of these objects are convective all the way from the center of the star to the photosphere of the star. And above 0.3 solar masses, they start to develop a radiative core, which is not convective. And that turns out to be quite important because stars with radiative cores do not mix the elements they're burning in the center. So that means that rather than simultaneously depleting all of the elements, the center gets depleted first before the outer parts have been depleted in the fusion. And another important point is that stars less than about one solar mass is about the lifetime equal to the age of the universe, and stars less than about 0.6 solar masses end their lives, we believe, as helium white dwarfs, except that single stars less than 0.6 solar masses, none of them have yet ended their life. So we do not actually have any observational evidence for that fact, but that's a theoretical fact. For stars more massive than 1 solar mass, some of them have ended their lives in the age of the universe, and so we think we understand their endpoints. Now at about somewhere between 1.5 and 1.8 solar masses, depending on the details of your model, there's an important division, which is a division in two senses. One is that below that limit, the dominant fusion reaction is by proton-proton, which is the dominant source of fusion in the sun, hydrogen fusion in the sun. And above about 1.5 solar masses, the dominant source of energy is through the CNO cycle, at least for stars which have finite amounts of heavy elements. The CNO cycle, of course, is much more temperature sensitive, so it produces a much more essentially concentrated core. And there's another difference which occurs around 1.5 to 1.8 solar masses, which is that at the end of the hydrogen burning, you have to ignite the helium, and these stars have degenerate helium cores in their late evolution, so when the helium starts to ignite, since the core is degenerate, the temperature goes up, there's no change in the pressure, since the pressure is all from electron degeneracy pressure. And if the temperature goes up, the nuclear reaction rates for helium burning goes like the 40th power of the temperature roughly. If you jack up the temperature by a factor of 2, that increases the nuclear reaction rates a lot. And so the helium in the center of the star ignites essentially explosively in the matter of an hour or so. Unfortunately, or fortunately, the total, by the time it's heated up the center, it hasn't fused enough helium to actually blow up the star. So if you were living in the center of the star, the helium flash, so-called, would be very exciting. The luminosity of the star changes dramatically in a few hours, the temperature rises up. But if you were sitting at the surface of the star, or beyond it as we are, the helium flash is not very exciting because it doesn't liberate enough energy to change the luminosity of the star very much, because it takes many millions of years for the photons to get out of the star. Now, above 1.8 solar masses, there's another difference, which is that unlike the low mass stars, because it's burning by the CNO cycle, which is very temperature sensitive, the center of the star has a very steep temperature gradient, and that means that the core becomes convective. So remember, below 0.3 solar masses, the whole star is convective. Above 0.3, the core is radiative, but the envelope is convective. The sun is a typical example. But above 1.8 solar masses, the core now becomes convective, and the envelope becomes radiative. So it's sort of inside out compared to the low mass stars. Now, the convective core is important because it means that as you fuse, all of the elements that are inside some core region are being mixed together. So their hydrogen fraction depletes uniformly throughout the core. So when you've depleted the hydrogen and there's no hydrogen left to run hydrogen fusion and you have to start helium fusion, there's now none anywhere within the core, and you have to go to outside the convective region in order to find some hydrogen to burn. So that's quite different than what happens in stars like the sun, where the hydrogen is being depleted at the very center, but when it's depleted at the very center, you just need to go a little bit outside and there's still some hydrogen, because it's been sitting there radiatively. So stars above about 2 solar masses have much more exciting ends to their core hydrogen burning. So below about 5 solar masses, after the hydrogen is exhausted, there's a sudden rearrangement in the structure of the stars caused by the fact that it now has to completely rearrange its structure in order to start burning in a shell outside. And the star then ignites helium burning in its center, and then when the helium starts to be exhausted in the center, it develops a shell which burns helium farther and farther out, and in that stage it's called the asymptotic giant branch star. Now above about 5 solar masses, it turns out that the centers of the stars are such low density and so hot that in fact they ignite helium non-degenerately, and there's actually no giant branch, no AGB at all, and the late evolution essentially occurs at a constant luminosity. Now at 8 solar masses, or 7 solar masses, there comes a big uncertainty. And the big uncertainty comes from the fact that at the end of helium burning, you're now left with a carbon core. And the carbon core below 8, at around 8 solar masses, stars is a degenerate carbon core. And for stars above 8 solar masses, the mass in this carbon core is large enough that the carbon core should ignite. But it's a degenerate carbon core, so it's very much like the helium flash, that the carbon would start burning, and it would liberate enough energy, raise the temperature. There's then no change in the pressure, so there's no expansion of the star. The carbon burning rate goes like T to the 60th power, so you double the temperature, and there's a big change in the carbon burning rate. And the difficulty is that in order to raise the temperature of the core enough to make it non-degenerate, you've actually liberated enough energy to unbind the whole star. And we don't actually know whether stars of that between 8 and 10 solar masses actually manage to blow themselves completely up when they ignite carbon in their centers, or whether they don't manage to blow themselves up. And unfortunately, we can't answer. One way to tell would be to see if you could find a star cluster for which the turn-off mass, namely the mass of stars which are just now finishing their evolution, is a little bit bigger than 8 solar masses, and you then look and see if there are white dwarfs in them. And if there are white dwarfs, it's obvious that the stars don't blow themselves up. And if there aren't white dwarfs, then probably they blow themselves up. Now, 2 years ago, I would have told you we knew the answer, which is that there is a white dwarf in such a cluster. Unfortunately, that white dwarf turned out to be a quasar at redshift 1, sadly. So we still don't know whether these stars blow up or not. It was found in a cluster of stars in the Large Magellanic Cloud, and there was this blue object which looked just like the white dwarf, but shucks. Well, so anyway, so what happens between 8 and 10 solar masses is not clear, but above 10 or maybe 12 solar masses, again, the exact boundary is not quite certain, it's clear that stars manage to ignite the carbon in the center non-explosively. It's non-degenerate, and they ignite the carbon, and then they ignite neon magnesium, and then they ignite silicon, and then they've got to iron. And if you burn iron, that takes energy rather than liberating it, and so the star begins to collapse, and it manages, in many cases it appears, to blow itself up and leave behind a neutron star. Now, one feature of that blowing up, which turns out to be very important limitation in our ability to predict these rates, is that when the star blows itself up, the gravitational binding energy which is liberated is about 10 to the 54 ergs. And if you imagine that that were not liberated perfectly spherically symmetrically, you could ask how much momentum could you give to the young neutron star, and you can see that with about a 1% asymmetry you could kick it off at about 1,000 kilometers a second, and nature appears to do that. Young neutron stars are born with velocities of several hundred kilometers a second, extending up to about 1,000 kilometers a second. And unfortunately, those velocities are just a little bit larger than the orbital velocities of the binary stars in which they're born. And therefore, the typical thing which happens is that when you have a neutron star, or the star which is about to explode that you've nicely made in a binary star system, the neutron star is formed in the supernova explosion, and it's given a velocity which unbinds it, and probably 99% of the time the binary is unbound. So the systems that are of interest for gravity wave astronomers are the 1% where it happens that the kick velocity of the neutron star is in the opposite direction to the orbit, so it drops it into a lower orbit, or perpendicular to the orbit, so it doesn't change the angular momentum very much. It requires special orientation of the velocity in order to remain bound. Or it could be from rare systems that we can never hope to see, which are born with orbital velocities so small that they're much larger than the kick velocities of neutron stars, and therefore they're not unbound. In above 25 solar masses, it's believed that for isolated stars, the end states are black holes with masses of 4, 5, 10, 15 solar masses or so. Okay, on the next 2 pages, I just showed you some evolutionary tracks in temperature and luminosity for some of the stars, and just to convince you that there's actually observation to support that, there are some of the theoretical tracks shown on top of observed Hertzsprung-Russell diagrams of star clusters, and you can see the magnificent agreement which has been obtained after 30 years of work. And then over here I've plotted another Hertzsprung-Russell diagram, temperature, luminosity of the stars. For those of you who are not astronomers, notice the convention that the temperature increases to the left, not the right. Very important. The color index increases the other way. And on these lines, of course, from luminosity and effective temperature, L is 4 pi r squared sigma t to the 4th, so you can draw lines of constant radius. And I've drawn lines of 1 solar radius, 10, 100, and 1,000 solar radii, so you can see in what stages the stars get to be very large. And I gave you some plots of the main sequence lifetimes of stars as a function of age. And in the handouts for today, I gave you the sample evolutions for 3 stars, the 15 solar mass star, 5 solar mass, and 1 solar mass. And these plots show the radius of the star as a function of time. And so for 15 solar masses, you see the star starts off at about 7 solar radii and lives its main sequence lifetime, which is only 12 million years, 10 to the minus 3, the age of the universe, until it begins to not increase in luminosity very much if you look at these plots, but it gets cooler, it begins to expand. And it does that when it exhausts hydrogen in the center, and remember it now had a convective core, so the hydrogen is all exhausted simultaneously. The star has to expand to rearrange its structure, contracting the core, expanding the envelope, until it ignites helium in the center. And then it can wander back and forth a little bit, igniting successively carbon, silicon, iron, until there's a supernova explosion and the star ends up as a 1.4 solar mass neutron star. The next page shows the 15 solar mass star, which is a little bit more interesting, has a main sequence lifetime 10 times longer than the 15 solar mass star, so 100 million years. Exhausts hydrogen, again, it expands. And the reason I've written here Hertzsprung gap, and the reason it's called the Hertzsprung gap is that the star has to rearrange its structure when it runs out of hydrogen in the center. It has to rearrange its structure, and it does so on a thermal timescale. It's just however long it takes the radiation to leak out of the star is how long it takes to rearrange its structure. And that typically is a very short time for a star like this. That's a few 10 to the 4 years compared to the 100 million years it took to get here. So stars happily live here, but if you imagine looking for them, let's look at 5 solar masses. Okay, so the star spends 100 million years here, but less than 10 to the 5 years over here. And then it spends, you can see burning helium in its core, it spends about 40 million years. So for every 100 stars that you see on the main sequence, there will be about 4 over here, and 10 to the minus 4 in this region. That's why it's called the Hertzsprung gap. You never find stars there because they're evolving so rapidly that they never live there very long. And Einar Hertzsprung discovered that gap, and therefore it's named after him. Okay, now after the star has exhausted helium in its center, it begins to burn helium in shells from the outside, enters the AGB, and the radius now you see has gotten up to 1,000 times the radius of the Sun. Okay, so this thing is sticking out around the orbit of Neptune. The binding energy at the surface is extremely low. The temperatures are very low. If you look here, the temperatures have gotten down to a few thousand degrees Kelvin. And perhaps because of the formation of dust and the fact that the luminosity is larger than the Eddington luminosity for dust grains, these stars begin to have huge mass loss rates. And they lose most of their mass in a few tens of thousands of years until it ends up as a one solar mass carbon-oxygen white dwarf, which is the core of this AGB star. Sorry? Okay.